So yeah, it's good to be back here. This room. This is okay. All right. So I'm going to talk about monotone minimal perfect hashing. I'll tell you what it is. This is joined with Martin, who is here, and Bill, who is not here. The paper is available on arXiv if you want to take a look. Good. So what is this talk about in general? It's about hashing from the title. It's about data structure lower bounds mostly. I would say that it's more about information theoretic lower bounds than data structure lower bounds. I'll tell you the reason soon. But on top of that, it's a lot about graph coloring. So don't worry, you've seen me give, some of you seen me give so many talks about graph coloring here. It's not at all about related to those, so new topic, good. And through that, it involves some duality and linear programming. This part is a standard. We didn't reprove, or like we are not proving anything here, but it's still good to just have a recap of that in the context of graph coloring, okay, and use it in the lower bound. Okay. So what is this problem? Just the following. I give you an array A of n elements from a universe of u elements. Let's say numbers 1 to u. What you want to do, okay. And as like Huacheng was saying yesterday, we'll think typically, let's assume that u is some polynomial in n. Okay, so each of these numbers I can represent it with theta, log, and bits. Okay, good. And what do I want to do? I got this array. I want to be able to answer this query. You give me a number in the array, I tell you what is its rank. Okay, how many numbers are smaller than it in the array? Okay, good. How do I want to do that? I want to create a small and fast data structure to answer these queries. Sounds good? So this is the question. Any question here?
When you say rank, it's like you sort the numbers and then...
Yes, exactly. Like if my array is, I don't know, 1, 5, 7, you give me 1, I return 1. If you give me 5, I return 2. 7, I return 3. Okay, so this is it, the entire question. One thing why this name, I've not picked this name. Martin didn't pick it. I don't know who picked it. It's not the best name, but let's go over it, what is happening. Well, this D that we have, this data structure is a hash function now. Okay, you're just mapping n numbers, let's say, to n numbers. So it's a function. It is perfect because the numbers you're mapping to are like distinct from each other. So you're mapping to different numbers. It is minimal because you're only using n different hash values. Okay, and it is monotone because the only way your hash values are smaller than, like if A is less than B, if and only if your hash values are smaller. Okay, so that's where the name comes from. But again, just think of this problem. Good. All right, and for this talk, let me actually ignore the fast part. I want to prove a lower bound. I'm just going to focus on just the size of the data structure or the hash function that I'm going to need. Okay, and that's what I'm saying, that this is more about an information theoretic lower bound than actually a data structure lower bound. Okay, good. So what's going on here? Well, what is the trivial upper bound here? I'm just going to store A explicitly in n log u bits. Now, when you give me a query, I'll just go, maybe I sort it before storing it. I'll go over it, I figure out the index, and I return it. Okay, so that's the upper bound. And I mean, you can do things which makes it faster, but ignore time. We are talking about a space. What is the lower bound? Well, I mean, if you want to store A, you need n log u bits to store A. Okay, so I'm done basically. This is upper bound and lower bound. Thank you for that. So what's going on here? The thing is that this is not a lower bound for this problem. If you think about it, there's no reason for me to store A. Okay, there is no reason that my data structure is actually encoding A. Let's go back a bit here. You know, this is the problem definition. I give you a number from the array, you return me the rank. If I give you something which is not in the array, you can do whatever you want. Okay. So at least a priori, it's not clear that your data structure is encoding the input itself. So there's no reason that there is a lower bound. In fact, let me convince you that it's not just a priori, it's not a thought experiment, it's definitely true. You are not encoding your array. Let me show you one simple upper bound, which is going to be better than n log. Yeah, good. Okay. So let me say that I give you this array. I'm going to sort it. Okay. Then every log n number, I'm going to store them explicitly. Okay. Again, think of u being poly n, so log n is okay for me. So I'm storing n over log n numbers explicitly. Each of them requires theta log n bits. I can store them. Sounds good? After that, what I'm going to do is to hash every number in between using log n bits. Okay? Now, what will happen is that these hashes will be unique between the pivots. I have log n numbers between every pivot. Log n bits are enough to hash them to unique. It may not be unique across, okay, as you see. But that's not a problem. So now when you give me a query, what will I do? I'll just go ahead and find what are the adjacent pivots. So I'll figure out, oh, it's somewhere between these two. Then I'll compute its hash value. I'll go over these hashes and figure out which one is the number. Sounds good? So for instance, you give me this, what is rank of 32? I'll figure out that 32 is between these two numbers by comparing this pivot explicitly. After that, I'll compute the hash of 32. I can pick my hash functions to be small enough that I can store it. I can compute the hash value, and I figure out, oh, this is this index. Probably if I count from the beginning, I'll get 11, so that's the number. Sounds good? So in n log n bits, I actually can solve this problem. Good. And this is the space. Okay? Each of these ones, the costlier ones, I only store n over log n of them. And the cheaper one that I'll store for everything only requires log n bits. So n log n.
Super quick question. So is it like, I mean, I'm just trying to understand, because you're like using hash functions, this is still a deterministic data structure.
Yes, this is actually, if you don't care about time, this is just an encoding of these things. I say the hash function, take exponential time to find. I don't think you need exponential time even, okay? But for now, essentially, this is deterministic even. Good. Any other question?
You can presumably shave off some square root of log n factor here.
Good. You can shave off that. I'm going to show, oh, I'm not going to show. I'm going to state that you can shave off even more. Okay, good. But I'll be curious to see actually how you want to do exactly square root log n. I'll check with you after. Good. Okay. So let me tell you a bit more non-trivial things. So it's a result by these people. They gave this n log n. In fact, they show that you can implement it in order 1 update time. Okay? Or like time to answer each query will be just constant. You can do something. And more related to us, they show that in fact you can shave off another log factor also. So n log n. And here their update time is log n. Sounds good? So far this much saving was done. Let me say this thing. Apparently, this problem is, now that you can do this type of saving, it's actually very useful in practice. It's implemented here. If this means something to you, I wanted to write it here. I don't know what it is. Okay, so this is like, so it can be implemented. And if people here are interested in that, this is actually a practical solution. Okay. And it's also used in like for theoretical, in case in like pattern matching algorithms and things like that, because you know you're doing better than the trivial n log n, so this should be useful, interesting. Okay, good. So now what is the state of the art? So I can do it in n log n space using this result. And omega n space lower bound is actually not at all hard to prove. Okay, it follows from the lower bounds for any hash function, or if you think about it, it's really simple lower bound. For instance, communication complexity of index will give you this lower bound, or simple encoding. Omega n is really not hard to prove. Okay, so this is the state of the art. Good. So what are optimal bounds for this problem? And this has been open. People have asked this question, and that's what we are going to address. Okay. So turns out that actually this weird function is actually optimal for this problem. So you can prove that, or we prove that any data structure is going to require n log n bits for solving this problem.
No matter what the query time.
No matter what is the query time. So this is good. So not only this is true for randomized, for deterministic things that we are trying. This is randomized. This is true for randomized algorithms, even if I don't care about the space you need to store the random bits. In other words, suppose there's this tape of random bits that you have access to it for free. You don't even have to store it. And you can use that to create your data structure. And that data structure now going to have expected size.
But randomness is not shared between query.
It is shared. It is
It's
this
shared
tape.
between
Yeah, exactly.
query and
Yes,
process.
exactly. So the randomness is even shared. The randomness is for free for you, even if I don't care about that, which allow you to use this. Like now you're, okay, sorry, let me take a step. If you have to explicitly write your random bits, in such an information theoretic setting, you are basically deterministic. Because I will just enumerate over all the random bits you use, and I just store them next to you. So there's randomness there is not interesting. I'm saying that I don't care about, like, you don't have to write the randomness. There's this random tape that is shared between the preprocessor and the query algorithm. And even in that case, this lower bound holds. Sounds good? And so this is true even given unbounded computation time, answer your question. But that's why I'm also saying this as not that much of a data structure lower bound, but more of an information theoretic lower bound. So because I don't even care about query time, and we'll get this result. Good.
What was the word monotone in this problem?
Monotone is the output that you have is if A is less than B, because you're outputting the rank, the value you assign to those numbers is also going to be less. So D of A or H of A will be less than H of B as well.
The hash preserves the order.
In a minimum perfect hash function, you have to store the n items in an array of size n, and in this one, you're restricted to store them monotonically.
Make sense? Good. One other thing is that this bound is actually, so I was talking mostly about poly n regime of u. This holds for all values of u. So you will get n log u, and u has to be within this range. Okay, it has to be slightly more than n, and it has to be less than W exponential. The reason is you cannot expect this to hold after this regime. There is an n log n upper bound independent of size of the universe. You just hash everything. So anything after this, there is no way that the lower bound holds. Below n, you cannot have the lower bound. Okay, so it's somewhere like this. A small of one term is just hiding a couple of things. Okay, so the only gap that we have is this small of one term.
Can you say, so a little bit curious, was it required that the things are actually stored in an array in some order, or is it just any encoding of that supports, these queries, given something that I inserted, I can tell you the rank?
Good question. Let me
It's
see.
required that it not be stored in an array.
Okay, yeah, so it's just any encoding of that supports.
You don't have enough bits to store it
Yeah,
in an
but
array.
maybe it just
You
sounds
mean the
like
array?
it has to be in order or something.
No, that's the output you are giving. Your output has this order inside it, no? You're outputting a number from 1 to n. I'm implicitly simulating an array for you. Okay, sounds good. So the rest of the talk, I want to tell you how to prove this lower bound. And there are two parts to this. There is a very nice, breezy proof technique. It's very nice and cute, and everything is good. Then there's the whole mess of actually proving it. Okay. So I will spend more time here because it's nicer, and I'll tell you about this mess a bit. Okay. So I had a couple of slides here. I want to walk you through the things we tried, and then tell you what is the final answer. I spent a couple of slides on this attempt, and then I realized it's too much digression. I'm just going to go through it quickly. I'll tell you this attempt sounds good, doesn't work, basically. So what it is this reconstruction attacks, index communication, lower bounds, encoding something in the state of data structure. All of this means the following. Maybe I can find a way that I map any string of certain length to an array, such that if you create a data structure, given just the data structure, I can figure out what was the string. Okay? Then the size of the set of different strings that I use, there is this bijection with the set of different data structures that I have, and which give me the lower bound on size of the data structure. Does this make sense? Good. And this is enough to give you omega n lower bound. Okay, this is like the first approach. This will give you omega n lower bound. You can encode 2 to the n strings directly into arrays and give this thing. If you want, I can show it to you later. It's like one-line argument. This does not seem to work better. Okay? This sentence is, strictly speaking, quite wrong. Can someone tell me why this is wrong? This cannot hold. Whenever you have a data structure lower bound, you're necessarily proving something like this. I can just take the different data. If I'm telling you that I need n log, 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 n, so many different data structures, I can just look at the states of all these different data structure and like assign a string to each of them using some encoding that I want and do this reconstruction. Okay? The problem with that is somewhat backward. I first have to prove the lower bound and then come back and find this encoding. So what I say that this does not seem to work is that the technique is not good for you. Like if you want to just strictly speaking follow this thing, it is hard to prove the lower bound. Okay? So let me move on to attempt number 2. And let's look at it as a graph theoretic view. I want to define this conflict graph. Pick all the arrays, possible inputs. Okay, fix u and n, universe size and size of the arrays. Put all the possible arrays as vertices of a graph. Good? So this is all the vertices. This is my graph. And what are the edges? I'll add an edge between two vertices. Let's say these two vertices. If a single element appears in both of them, or if there is an element that appears in both of them, but in different positions. Okay? So I'll add suppose this element, I don't know, 5 appears in this array in position 5 and in position 10 in this one. Okay? Then I add an edge between them. Cool?
I don't understand the relation between what you said and what's on the slide.
Okay.
What is A of I?
A of I, you know the array, the vertices of this graph are arrays.
Yes.
Okay?
So A is a
Sorted
vertex.
arrays.
They're sorted arrays, yes. So there is a single number that appears both in A and in B. This AI, which is equal to B of J.
I see, but not in the same
But
position.
not in the same position. Exactly. I add an edge between them. Okay? Good. So now one simple observation is that if I have two vertices in this graph that are neighbor to each other, I should not encode them to the same exact data structure. Okay? Because if I do that, when I query that data structure for this intersecting element, the answer is different. It's like 5 in this one and 10 in this one. If they are mapped exactly to the same encoding, I will not be able to just use the encoding to differentiate it. No? Good. So then if I do this thing, this, like what is the size of the best data structures for these parameters based on this graph? You know?
Chromatic number of this graph?
Exactly. It's like log of the chromatic number. Okay? So now this is this graph question. Log of chromatic number is precisely the size of the best data structure for this problem. Okay, good. So far this is a standard, nothing fancy. Good. And yeah, this is coloring. Okay, so chromatic number is the minimum, the smallest number of colors I need to assign to the vertices so that no edge receives the same color on both its endpoints. Okay, so good. All right. So now what is going on? So basically now our approach is that I have this conflict graph. Let me go ahead and compute its chromatic number. And I really don't have a good name for this. This set system type graph, if you know a better name, let me know. But these type of graphs have been studied a lot in discrete math. I'm citing just one line of work on a very particular set of graphs. Okay, there are tons of other things. These graphs that I'm citing, these are the ones on shift graphs introduced by Erdős and Hainai. So what is going on here? Let me show you an example. So the graph is this thing. It has exactly the same vertices as the conflict graph. Meaning sorted array of length n from a universe size u. What are the edges? The edges are a subset of edges of the conflict graph. You only add an edge if it's something like this happens. Basically, you have a shift. This array A1 to AN, you throw out the smallest number and you add the larger number at the end of it. Okay? This is a subgraph or an input. There are tons of elements now that are shared between the two arrays, and none of them appear in the right position between the two of them. Okay, so there is this notion of a shift graph. And the nice thing is that they prove that these graphs have non-trivial chromatic number. Their chromatic number is iterated log n minus 1 time take log of the universe size. Okay, and this is tight, upper and lower bound up to this step. Sounds good? So what does this thing mean for us? And emphasis, this is iterated log. This is not to the power. Okay. So what does this thing mean for us? This graph is a subgraph of the or conflict graph. So we have that our chromatic number is this much. Okay. This means that if I take my universe to be large enough, I'll eventually get a lower bound which is strictly more than n. Okay, so I can eventually go over this encoding type argument, I can get a small omega n lower bound. The catch, of course, is that I have to take my universe to be some power of 2 and just go all the way there to be able to get something. Okay? And if I do that, I don't get n log u lower bound. Even in that case, I'll just get this. But there's still something non-trivial for not the most interesting setting of the universe size. Okay, good.
Didn't you say that for every u there is an upper bound of n log n?
I think I said that.
So I think the hash function.
But it's omega n, no? A small n log n is more than omega n.
Right, but if I take u large enough, can I get like?
I think in that solution, the hash function itself will have a problem also. Like I have to map, so maybe n log n wasn't strictly speaking true. I have to store the hash function somehow.
The hash function will have a term like log u bits.
Yes. Yes. And interestingly, this chromatic lower bound does not apply to the randomized version that I told you. This technique does not give you the randomized lower bound, even though our third attempt will do. Okay, good. Okay, so what are the problems with this approach? The universe size has to be ridiculously large. And even that, you don't get the tight bound, but you get something. This does not apply to randomized data structure that I wanted to do. And a very subjective opinion is that chromatic number is not the easiest thing to work with. Okay, it's not, I mean, I'm saying it in this talk. I think in another talk I would have said otherwise. But here, it's not the most fun object to work with. Okay? So these are the problems. So what do we want to do? Before moving on, let me tell you how we decided to come up with the third approach. Was through fixing this thing. Okay? And if you think about it, there is a very natural fix to this thing. Okay? So how do I do that? I'll apply graph product. Okay? Instead of applying this argument to the entire graph, I create a smaller graph, shift graphs, and then pack all of them inside one conflict graph. Okay? So let me say it roughly like this. Let's say I create a small shift graph, okay? And then I'll take this OR product of them. Think about, I'll show it to you actually, the product in a second, to get one conflict graph. So I have these small graphs on n parameter n0 and u0. I create this k times n0, and the universe time become k times more also. Now think of n0 and u0 to be just a slightly super constant. Okay, all the largeness of n and u are now inside this k. Okay, they're just a slightly super constant. Okay, good. So what does it mean? It means that I'm going to mark my universe or color it, but this is a different coloring. Okay, I have this green part of the universe, the red, the purple side. Okay, and the way I create my graph is that I'll add an edge between two vertices if this green part and this green part have an edge according to the shift graph, okay? Or maybe, or this red part have an edge according to the shift graph, or the purple side has an edge according to the shift graph. So my graph, the vertices are product of k different shift graphs. The edges are or between them. If between this tuple, if even one of them have an edge, I will add an edge between the two. Sounds good? So if I do this thing, I'll get this type of parameters. And now we can say in this other, like if n0 is log a star of u0, I can get a lower bound chromatic number of the shift graph will be strictly more than n0. Okay, this theta is like some large constant, 100 log a star. and I'll get something which is better than n0. This n, good. And you know, I said that n0 and u0 are like, they are slightly super constant. Think of them, they are again around log star of n. So R, the largeness of n and u is coming through k. So u and n will be polynomially related to each other. Okay, good. So if I do all this thing, I need the following property. If it so happens to be the case that the chromatic number of this shift graph is the product of, the chromatic number of this product graph is the product of the chromatic number of each of its components, then if you do the algebra, you will get something which is a strictly more than n, omega n lower bound will get something for even a smaller universes. Sounds good? Okay. What is the problem? Chromatic number is not really fun. This is actually not true. It's not true in general. It's not even true for shift graphs. Okay? It does not behave in this product manner. So this is not true. So actually, this approach will not give you any lower bound. Okay. Sounds good? So now, I suggested a fix, which actually doesn't work, so we don't have the fix. But let me still say that, let me change this thing and say that chromatic number does not have this direct product property. Okay. So now I have these three problems with chromatic number. What should I do? Yeah, relax it. I want to now, to fix this thing, there is like the natural ways to look at the relaxation of chromatic number, and that's what we are going to do. This is that we are going to look at the fractional chromatic number, and I'm going to define that and talk about that. And that's the part which is everything is nice, everything is like known. You can use lots of good result here to do this. So what is fractional chromatic number? This is any graph. It has nothing to do with conflict graph or anything. In any graph, let me define a bunch of things. This is like I of G is the set of all independent sets in G. Okay? And I of GV are all the independent sets that contain vertex V. Now, fractional chromatic number, one interpretation is the solution to this LP. Minimize, so pick an assignment to the independent sets of the graph. Okay, minimize the sum of the assignment such that you cover every vertex. Okay, for every vertex, you have put a mass of at least 1 over the independent sets that contain that vertex. So this is the LP. Let's think about it. Why is this a relaxation of the original coloring problem, or like chromatic number?
Combination of colorings, right there.
Yeah. Yeah, or think of it even like directly. Why is this a relaxation? In coloring, what are you doing? You are picking, each color class is an independent set. You are picking C different independent set such that each vertex belongs to one of these independent sets. Okay? Just pick any integral coloring, put a mass of 1 on that independent set corresponding to each of its color classes, and put 0 everywhere else. Here you will have C colors. This sum up to C, and here every vertex belongs to exactly 1 independent set, so you covered every vertex. So this is really like a truthful relaxation of graph coloring. And just to make sure, this is MP hard to calculate this thing. This is a huge LP and everything. Okay. So the observation is that chromatic number is smaller. In fact, it's also not that much smaller. This is just a simple randomized rounding. The same thing you do for set cover will also apply here, and will imply that you are within log factor of the number of vertices in the graph. Okay. So fractional coloring closely enough to the integral coloring, and is a lower bound for that. So what we can do is to use fractional chromatic number of this conflict graph for our purpose. Sounds good? And yeah, on the surface, you can always ask this question, but this is even a weaker bound. Why should it make things easier? But that's not valid. I mean, we know when you go to relaxations, life becomes easier. Okay? So in fact, let me go over the problems that I mentioned. The problem with chromatic number was that it does not have direct product property. Fractional chromatic number does, actually. Okay? It does not apply to randomized data structure. You can actually use fractional chromatic number to even lower bound randomized data structure. And this requires an argument. It's not trivial, but it's not hard. In fact, the argument is very similar to the easy direction of Yaw's min-max principle. Okay. And chromatic number is, okay, not fun to work with. This is easier to work with. Okay, fractional chromatic number, there is a good reason that it is easier. Let me tell you. If I give you a graph, if you want to lower bound its chromatic number, what is the easiest thing you can do? Like, what is the natural thing you do when you want to say that this graph has a large chromatic number? Yes, you find a clique in it. But there is a huge gap between clique and chromatic number. Okay? In fractional world, you can look at the fractional clique, and fractional clique is equal to the fractional coloring. Okay? So your task become a bit harder. You have to find a fractional clique, but now it's equal to the coloring number. So you'll get actually tight bounds. And that's what we want to use here. So this is the dual view. The dual of fractional chromatic number is fractional clique. It's the following maximization problem. Assign a value to the vertices of your graph such that from every independent set, you only put a mass of 1 on the vertices there. Okay? Why is this a relaxation of the clique number? Well, in an integral clique, just let y of it be the characteristic vector of that clique. You never pick 2 vertices from an independent set. Okay, so you satisfy this. So this is a relaxation of the clique, basically. And a strong duality tell you that fractional coloring number is equal to the fractional, clique number. And that's what we want to use a lot when we are using these things. Good. So one implication, it follows from this that the product is equal to the product of these two numbers. Okay, so if you have a graph product between them, the fractional chromatic number of the graph product is just the product of each term. Okay, I'm 100% sure this is known. I could not find a reference for this thing. So there was a book on fractional graph coloring. They prove it for all sort of graph product except for this one. If someone knows a reference to this, let me know. I don't know. There is absolutely no way this is not known. Okay, good. So the good thing is that now we can apply inverse size reduction. These are now equal. That idea that I told you, we can just apply it there. The other implication is a very nice interpretation of the chromatic number through this thing. Let me parse it. If my fractional chromatic number is equal to the following, maximize over all distributions assignment to over the vertices of the graph. Okay, so figure out any distribution which is an assignment to the vertices of the graph. There, go over, so for any distribution, look at all the possible independent sets. What is the probability that if I sample a vertex according to that independent set, it belongs, according to that distribution, it belongs to this independent set? Okay? Think about it. Find the distribution so that no independent set is likely under that distribution. And you see this is a maximization. So any distribution is a witness toward a large chromatic number. No? So my task is to find a distribution such that no independent set has a high probability under that. And by the time we were here, this really looks like Yaw's min-max. I'm giving you a distribution over inputs problem so that no independent set has, or like there is no data structure that can cover lots of different like inputs. Okay, good. So this is what we are going to use, this type of formula. So what is our approach is that I'm going to create a conflict graph. I'm going to pick the conflict graph for this setting of parameters. Okay, 2 to the 2 to the n square. I'm going to look at this formula and create some distribution over input arrays. Vertices here are input arrays to the problem. Independent set of the graph, they are actually functions that map the universe U to numbers n. Why is that? In this graph, I had an edge between any two vertices if a single element appears in two different positions. So if I have an independent set, an element can always appear in a fixed position. Okay? In an independent set, an element either does not appear inside the array, or if it appears, it will always appear in a fixed position. Okay? So independent set of these graphs are functions, basically, that maps each element to where they should appear inside the array. Good? Good. So the key technical lemma that we prove is that for this setting of parameter, there exists a distribution such that any function that you pick, the probability that that function maps every number to the right position that you wanted. So I pick ai's randomly, f is fixed. The probability that f of ai is equal to I for all of them is like less than this number. Okay. Sorry. Roughly speaking, this means that the probability that this is a distribution over vertices of the graph, any fixed independent set, the probability that if I pick a vertex from this distribution, that vertex belongs to the independent set is less than n to the minus n.
So you get a lower bound of n to the omega n?
Good. So this will give me that my chromatic number has to be n to the omega n. Okay? So let me move this. Good. So my chromatic number has to be n to the omega n, my fractional chromatic number, which means that log of fractional chromatic number will be n log n. For this parameter, this is n log 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 u. So for this particular universe size, I can get this lower bound. Sounds good? So if I have this lemma, I can get this thing. And now, it's not that bad because, yes, the universe is crazy, but now I can apply that graph product idea. Okay? Fractional chromatic number allows me to do this graph product and just move this range of parameter u to whatever I want. Okay? So this means that this will hold actually for all this range of u that I was interested in. So the nice part is that when you go through this fractional chromatic number and essentially you basically follow your nose at this point, it brings you to here. Okay? Now the goal will be to prove something like this. Sounds good?
Quick question. So where does the argument fail when u is super small or super large?
This distribution, the distribution is really based. Oh, you mean the graph product?
Yeah.
I mean, you have k times u base. So let's say size of the new. Let me just say it. So your new parameters are like k times n0 and u is k times u0. Okay? The lower bound you get are things based on this thing. Okay? So the superlinear part of the lower bounds come from the superlinear part of n0. Okay? So if I make these two things to be equal to each other, let's say I set k to be exactly equal to n, my lower bound will become omega k. I don't get anything superlinear.
Yeah.
So I cannot make my universe be very small as well.
So, but as long as n0 is something slightly super constant, u0 also becomes more super constant.
Yes.
But in this case, like u and n seems like it can be arbitrarily close.
They can be, but then you don't get the exact n log 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 u bound. Then you just get a small omega n lower bound, no? If this thing is super constant, it should be n0 should have a property that log 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 n0 is the same as log 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 u. Make sense?
Oh, I see.
Good. Good. Any other question? Okay. So let me very quickly hand wave my this lemma. I don't think I can do it actually, but this is the mess. This is the part which is okay. So I just want to show you roughly how does the distribution look like and completely hand waving through it. Okay. So I have to give you a distribution over the arrays. I'm fixing my universe. This is universe u. I'll have this notion of a sampling range. For now, I set it equal to u, and I'll show you what is this. Okay. So my first element.
Sorry, some more basic questions.
Mhm.
of these details. An array is just a subset of U, right?
Yes.
So this is just a distribution of a subset of U. Why not pick a random subset? That will not work?
No. No, this distribution is very far from uniform. No, random subset is not good, really. No, that's a good question. We've not tried so many different distributions, but random for sure will not
Okay.
give you that.
Is there a short reason why?
Let me give that to you offline. Yes.
Can you
Well, if it's
somehow
quick, I'd also like to hear it. I think what you're saying. So
Uh,
Could you
I.
write
c-
down-
oh, that's fine.
maybe what the requirements?
Yeah, they can do that.
Let
I
me
mean,
good.
It might be good to write it down just because.
Yes.
So we, because I expect I'll have to look at it at least 10 times.
Sounds good. Basically, this lemma, yes? And me-
So you're writing that you have a set of, you have a distribution of requirements.
I'm picking n numbers, a1, a2 to an. This is a distribution over this thing. I have a fixed function f that maps u to n. This is fixed. Okay? I want to have that probability that.
Use switch markers.
Of course. This is f of. I want probability that for all I, f of ai is equal to I. Good.
Now,
So
I forget something very basic. The A1 through AN are ordered or not?
yes. Yes.
So I'm increasing them.
Yeah, so that's why it's just a subset.
This is just a
One.
subset.
And you want for every f that this probability is small.
Yes. Good.
is the short argument? Sorry, is the short argument why uniform doesn't work? Is
Your f is decreasing, basically.
yeah, so you can kind of have an f that's the first n fraction maps to 1, the next n fraction maps to 2.
Perfect.
And then it's 2 to the minus n instead of n to the minus n.
Exactly. Good. Yeah, 2 to the minus n is easy to get for the. I think most distribution will give you 2 to the minus n, will give you omega n. That's the good, that's why omega n is not hard to prove. The thing is to, I want a log n factor more, okay? And that's, I need an n here. Yeah, good. Thank you. Okay. So let's go over this yeah.
Could you
Gotcha.
just say, I didn't follow.
Oh,
what it
so why shouldn't I just pick A uniformly? Okay, what will happen if I pick A uniformly? And I think he's saying that the probability that I'll get will be 2 to the minus omega n only. For what type of an f? I guess f should map the first 1 over n fraction to 1, the second 1 over n fraction to 2, and so on and so forth. Okay. The probability that you can skip that, or the probability that you are there will be just 2 to the minus omega n, I think.
Where did the 2 come from?
What should?
Constant 2 minus n. I don't know. It's just counting.
So the expectation of the ith order statistic is what is I over n, and I don't know what the variance is off the top of my head, but it might be that it means that the probability of going outside of the segment is only constant.
Yes.
Yeah, and you're picking them in a sorted order also. Yeah, good.
I guess you can also just count how many arrays there are of that form, divided by the total number of arrays, and then I think it's pretty easy to see if some constant to
I'll do that offline. I'll
Yeah.
confirm with you. Yeah, this is exactly that. Good. All right, so let me take 5 more minutes to try to say something which sounds a bit intelligent about here. Okay, good. So this is my universe. I have this notion of a sampling range. I'm going to sample from something like this. So my distribution is going to be very non-uniform, in fact. So what I will do is that my first number, I just sample it from the sampling range uniformly at random. So my first number lands somewhere inside the universe. Okay. Then I'm going to randomly shrink this range to something smaller, and I will roughly tell you how we are shrinking this thing. So now I'm in a smaller range. I look at this range in front of A1. Okay, I'll put that sampling range here, and now I pick uniformly from that sampling range. So my next number will become here. Then I will randomly shrink this, not uniformly randomly. This shrinkage is a highly non-uniform distribution. Okay. Again, it will shrink to something smaller. The third number I'll pick randomly from there. And these distances are becoming smaller and smaller. So my numbers are becoming concentrated closer and closer to each other. Eventually, I'll sample up to my last number. Okay? The distribution has this nice thing that, in fact, all the way to even AN is more or less inside the sampling range of A1 itself. Sorry, A2. So remember when I was sampling A2, I put a range in front of A1. Almost everything after that will come from that with a very, very high probability. So it's something like this. The scales are like entirely off here. These ranges are becoming doubly exponentially smaller. That's why those parameters will show up, so that we can get these properties. And they're highly non-uniform. I put this thing here just to show the distribution is nothing that crazy. Okay, like it's not like the description is not 5 pages. This is the description. Okay.
So could we go back to the previous slide?
Yes.
So somehow I just lost the whole picture. So you were trying to describe a distribution over
these n numbers.
over these arrays, which is subsets. Okay. And you're generating the things one at a time
Yes.
sequentially?
Exactly.
So say again what
So roughly speaking, the way it works is that I first pick my first number uniformly from everywhere. Then I'll shrink the range that I'm picking to somewhere in front of A1, and I'll pick uniformly from there
to some interval.
to some interval. I pick the next one from there. Then I'll shrink that range even further to something much, much smaller in front of A2, and I sample from there. I each time shrink to something much smaller, and then I sample from it. Okay? And these numbers, if you can see, they like the first one goes from very long range. The distances become smaller and smaller over time. Good. Omri, how much time do I have?
Supposed to finish 4 minutes ago, but
Okay. So how much time do you want me to have? More like?
let's try to wrap up in 5 minutes.
Sounds good. Okay. So this is the distribution. Something very quick about the analysis that I want to tell you. So our goal is to get this type of a property. No? We are going to partition this sampling range in front of, at any iteration. This is an argument we apply it at every iteration separately. At each iteration, there is a hierarchical way of partitioning the interval you are sampling from into 2 parts. This is not hierarchical. I didn't draw it hierarchically. Okay? And for all my discussion, this part does not matter. But for technical reason, this has to be hierarchical, different levels. So you partition this interval in front of you to either some parts, these red parts, these are sparse. These intervals, only a small f maps very small number of entries to I. Remember, my goal is to get f of ai equal to I. And this interval is such that few of these entries have that property. Less than 100 over n fraction of them are mapped by f to I. These are numbers. Very few of them are mapped to I by f. Okay? And remember, this is the goal I want. Okay?
This is for any f you want.
Yeah, f is fixed.
Oh, sorry, f is fixed.
F is fixed. I'll apply this thing for each f individually. So f is fixed. This is an interval that f does not map many of its numbers to I. if I tell you that AI is chosen uniformly from a red interval, I'm in a very good position. Why? Because no matter what has happened so far in the past, the probability that f of AI is equal to I will be low. AI is chosen uniformly from inside the red intervals. The red intervals have this property for only a small fraction of them, so everything is good. Okay? So this is a good event. If this event keep happening over and over, the probability that my f maps everything to the right place become n to the minus omega n. Okay? So if I can maintain this property for constant fraction of the elements, then I'm happy. But this was assuming AI was chosen from the red interval. What if it is chosen from a green interval? And green intervals are dense, basically. The nice thing about the distribution is the following. If AI is sampled from the green part, because I was packing these things next to each other closer and closer, the final range that I had will also be more or less sampled from a green part. Okay? Define the final range. These things are getting closer and closer. They are similar to each other. So if my AI is sampled from a green part, that final range also will be sampled from green part. This is not correct. That's why I needed a hierarchical version. That's the part I'm lying. But more or less is that AI will be sampled from here. All the way to AN will be sampled from here. And this final sampling interval will be part of this green part as well. Why is this a good thing? Look, the green contains lots of I inside it. Okay, like F maps lots of element to I there. So my interval, my final interval is collecting lots of I inside it. Like 100 over n fraction of this final interval will be I. Okay? So this means that this cannot happen many, many times. This interval is collecting numbers, basically. And whenever it is sampled from a dense interval, it collects lots of I inside it. If this happens another time, it will collect lots of I plus 1 inside it. Then it will collect lots of I plus 2. This thing cannot happen more than n over 100 times. Okay? This is the entire argument in the paper. The rest of the paper is 5 pages. This is like the rest of 20 pages. Okay? So I pushed through it very fast. The summary is that basically there is this potential function argument for all but n over 100 iterations. No matter what has happened, the probability that I get will be 100 over n. Yes?
You have 5 minutes, so I don't want to use it for time.
Okay.
I'll ask later.
All right. Sounds good. So let me conclude then. The key technical lemma was this thing. This is not graph theoretic or anything. This is like a property of set functions and distributions. Like that, you'll get this. This will tell you fractional chromatic number of the conflict graph is n to the omega n. So size of the data structure will become this thing. We said it's log of this quantity, which is this. And we can extend it to all universe sizes using this graph product idea because we bounded the fractional chromatic number. And this gives us the final result, like n log 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 n bits for this problem. And this is tight. This works again for all universes. You're good. And yes, thank you. Do I have time for questions? Or?
Just very quickly, on the green and red intervals, the stencil. So I think that maybe you said this, but so it's that you choose the red intervals first, and the green is what's left over. So any interval where there's a sparse number of i's, that's you just create a red interval.
Yes.
These maximal red intervals.
Yes.
And whatever's left you color green, and that means that a green guide not only is dense but has no sub.
Oh, good. Yeah, perfect. Yes. This random shifting idea that I was saying is not enough that if you pick a small interval from an large interval which is dense, will not imply that your small interval will be dense also necessarily. That's why we need this hierarchical version that this dense part not only is dense, it doesn't have any dense subpart inside it. Any sparse subpart. Yeah. Thank you. Yes. Good. No questions? All right, perfect.